Hello, I'm William James Martin, and I'm going to demonstrate 5 different proofs of the infinitude of the prime numbers. So, first of all, we have Euclid, and this proof is 2,000 years old. So if we take the prime numbers 2, 3, 5, and so forth, up until what we presume is the greatest prime, and observe that all of the primes, of course, divide this product. If we add 1 to it, however, then none of the primes will divide this product, plus 1. For instance, 2 will not divide it because it's an odd number, and similarly for 3 and 5, and so forth. So every number is divisible by a prime, and this is no exception. So this has to be divisible by a prime which is not in the original list. Okay. If we call this Q, then the next prime we're able to find should be less than or equal to Q. And even though Q is a very large number, much larger than P sub n, still it's an upper bound. So still it's something. Second we have Euler. So Euler observed that the harmonic series, n equals 1 to infinity, can be rendered like this: 1 plus 1 over 2 plus 1 over 2 squared, so forth. 1 plus 1 over 3 plus 1 over 3 squared, and so forth. 1 plus 1 over 5, 1 over 5 squared, and so forth, and so forth. Without prejudice to how many of these prime numbers there are, or however how many there are, should generate the natural numbers. This can be written as, this is a geometric series, so this can be written as set of P contained in the set of primes, P contained in the set of primes. So this can be written as 1 minus 1 over P inverse. In other words, P contained in P, 1 over 1 minus 1 over P. This is the closed form of the geometric series. Equals P multiplied top and bottom by P, P minus 1, P contained in P. Now the series is a harmonic series, and we know that diverges to infinity. Therefore, the right-hand side also has to diverge to infinity. Therefore, there has to be an infinite number of prime numbers for this to happen. Okay. That was Euler. Next we go to Racine. Who enunciated the concept of the Racine prime. And this would be a number of the form 2 to the n minus 1, or 2 to the p minus 1, if you take that to be a prime. So I claim that if there is a prime divisor of this number, it will actually be greater than p. So if we think maybe we found the greatest prime, then we can show that there's a greater one. So every number has a divisor, prime divisor, so let that be q. So then q divides 2 to the p minus 1. In other words, 2 to the p is equal to 1 mod q. Right. This left-hand side is a definition of the right-hand side. So in other words, P2 has order P in the group Z mod QZ, multiplicative group 2 mod Z, 2 mod 2Z, take away 0. And by Lagrange, by Lagrange, the order of any subgroup has to divide the order of a group. So in other words, P has to divide Q minus 1. In other words, p is less than q. So any prime divisor of a Racine number is actually greater than this exponent, be it prime or otherwise. Okay, so we failed to find the greatest prime in p. We've shown that there is another one. So now we turn to Fermat. I'm up to 4, I believe. Fermat, as I know, as I'm aware, does not have a proof for the infinite number of primes. But he did enunciate the so-called Fermat prime, which it turns out is not really a prime. That's 2 to the 2 to the n plus 1. Fermat calculated this for n equals, up to n equals 4. And at n equals 4, that's still a very large number. It's in the neighborhood of 600,000, I believe. And determined them all to be prime. And he conjectured that these would all be prime numbers. It turns out that they're not. Euler was able to calculate it for n equals 5 and determined that it was not a prime. Nonetheless, we can show that given two Fermat numbers, and f sub n and f sub n, f sub n and f sub n, that they are relatively prime. In other words, they have no primes in common. If that's true, then we can generate an infinite number of prime numbers as divisors of these terms. We can generate an indefinite amount of those. So to prove that, we need the recursive formula, which is this. Let k go from 1 to n minus 1 of f k. And that's equal to fn minus 2. Now, why that helps is if m is less than n, then f sub n will be a factor of this. And if it has a prime divisor in common with f sub n, then that prime divisor will also have to divide 2. However, Fermat numbers are odd, so that's not going to happen. So we need to prove this recursion. So let's write f n minus 1, k equals 1, fk times fn. Okay, so by the induction hypothesis, this is going to be equal to fn minus 2, right, times fn. And that's going to be equal to 2 to the 2, so this will be 2 to the 2 to the n minus 1 times 2 to the n plus 1. Right. 2 to the n plus 1 is f sub n, and we're subtracting 2 here, so this becomes minus 1. So this is the difference of two squares, so we get 2 to the n squared minus 1. And this is equal to 2 to the n plus 1 minus 1, which is equal to 2 to the n plus 1 minus 2. Right? And the part in parentheses is a Fermat number, it's fn sub 1. So this is fn plus 1 minus 2, which is actually our induction hypothesis that we sought to prove. Okay, so we turn to Dirichlet, 5, I guess. So Dirichlet took Euler's proof a step further. And we denote the zeta function to be the summation of 1 over n to the s, n equals 1 to infinity. And we need to keep s greater than 1. If it's a real number, Riemann introduced the notion of S being complex, so that's possible too, if S is complex, but in that case, you need to keep the real part greater than 1. Otherwise, it diverges. Right? When S is equal to 1, that's the harmonic series, which diverges. So that converges for S greater than 1. So let's take the logarithm of both sides. So the log of zeta S should be equal to the log of that, and I forgot to mention, and I'll do it right now. This is equal to pi 1 over 1 minus 1 over p to the s, p containing p, by the same argument that we used originally, spinner-based, but it's the same argument with the difference that we have an exponent of s. Right, this is Euler's formula. Okay, that's equal to, let's write it this way, pi p containing a set of primes. P to the s, p to the s minus 1. Okay. Actually, I don't think that's necessary. Leave it like this. Okay, so we take the logarithm of both sides. Okay, so the log of zeta s should be equal to the log of pi, p contained in p, of 1 minus 1 over p to the s inverse. And if you recall from calculus, that has an expansion, the logarithm has an expansion. This is equal to, the log of the product is equal to the product of the sum of the logs, right? So this can be written p containing p, and summation n equals 1 to infinity, 1 over n p to the n s. That's the expansion. That's the expansion of the logarithm. Let me write, let me just show this interchange. So I left out a step. So this would be, the log of the product is the sum of the logs. So let me just write 1 minus 1 over p to the s. Okay, and this has an expansion. This is equal to summation p containing p, summation n equals 1 to infinity of 1 over n p to the n s. Okay. Recall that expansion from calculus. All right. So let's get a bigger sum. This is going to be summation p, p contained in p, summation 1 over p to the ns, where we drop the p, we drop the n, making the denominator smaller and therefore making the reciprocal bigger, so we have a bigger sum. Okay. And n equals 1 to infinity. And let's separate the case n equals 1. So then we have summation p containing p, summation n equals 2, infinity, 1 over p to the ns, plus summation p containing p, 1 over p to the s. Right? Where I separated the case n equals 1. We started here with n equals 2. So we got a bigger sum when we did that. Okay, let's look at this sum. Let's look at that. So, okay, so we can write this summation p containing p. Give me 1 second. So we can write the summation like this. That becomes the closed form of this is going to be 1 over 1 minus p to the s. And I need to factor out the 2 in case 2. So this is 1 over p to 2s times 1 over 1 minus 1 over p to the s. All right, that's the closed form of this expansion. Okay, multiplying by one of those available p to the s's, we get p contained in p. 1 over p to the s times p to the s minus 1. Right. Where I multiplied one of these p to the s's through the denominator. Okay. So we can make a bigger sum by replacing p with n, because the primes are a subset of the natural numbers. So then we have starting n equals 2. The first prime is 2. So we're justified in writing starting with n equals 2. So this is going to be 1 over n to the s minus 1. And we can make that bigger still by taking s to be 1. That makes the denominator smaller and the reciprocal bigger. So this is equal to summation n equals 2, 1 over n to n minus 1. Okay. That can be rendered summation n equals 2 to infinity. That can be rendered as 1 over n minus 1 minus 1 over n. Right, just separate that fraction into 2 parts. Okay. And n equals 2, this will be, we'll get 1, right? 1 over 2 minus 1 is 1. Minus 1/2. I should have started here. We get 1 minus 1/2. At n equals 3, we get plus 1/2. Minus 1/3. And then plus 1/3. And so forth. This is a collapsing sum, and it's just equal to 1. Okay. So what do we have? We have the logarithm of zeta s is equal to the summation of p contained in p, 1 over p to the s, plus 1. And that's an inequality, right? Because of this. Or the log of zeta s minus 1, subtract 1 from both sides, is less than or equal to the summation p contained in p, 1 over p to the s. And that's less than or equal to the logarithm of the zeta function. Right? Because the log of zeta s, because the log of zeta s would be equal to all of this. Left my mind. If we put the n back in here, then these are equal. We have equality. So then the log of zeta s would be equal to these two terms, and it's certainly going to be bigger than just one of the terms. Right. So we have the summation of 1 over p to the s bounded between the log of zeta minus 1 and the log of zeta plus 1. So, and we let s go to 1 from the right. We know that the log of zeta s for s1 is a harmonic series. This is the log of the harmonic series. So the harmonic series diverges, and both of these bounds diverge to infinity. Therefore, the summation of 1 over p is equal to infinity. Right? That happens when we take s to 1. Okay, so these are the 5 proofs of the infinitude of primes. There are others, but these are some interesting ones, I think. Let me just mention a couple more things. which I'll only mention, there are infinitely many gaps. Infinitely large gaps as a system of primes. And this is proof by example. So if we take 10 factorial and add 1, and then 10 factorial and add 2, and so forth, 10 factorial plus 10. All of these numbers are composite, because, except for the first possibly, because this is divisible by 2, the next one will be divisible by 3, this is divisible by 10. So we have 9 consecutive composite numbers. Well, I didn't have to choose 10, I could have chosen a billion or a trillion. If I had chose a trillion, I would have gotten a trillion consecutive non-prime numbers, composite numbers, minus 1, a trillion minus 1. So, proof by example, I think that's convincing. And just one more thing I want to mention. And that's Bertrand's postulate. I don't know if Bertrand actually proved it or not. It's called a postulate, but it can be proved. The proof is elementary, but it's also very involved. It would probably take me a half hour to do it or more. But this says that there's always a prime number between n and 2n. Right? For every n, there's a prime number greater than n but smaller than 2n. So this puts some constraint on the growth of prime numbers. Even though there are infinitely many or arbitrarily large gaps between the prime numbers, still we have this constraint. Let me write this formally and then I'll conclude. So for every n, there exists a p containing a set of primes such that n is less than p less than epsilon. Okay, so I've shown you 5 proofs of the infinitude of the prime numbers and also mentioned a couple more results. So that concludes this discussion.